let's try the dense sample. So what I did was starting thusFit. Then I go to File and select Single Dataset, because that's the most simple one. I get the window for a new file and click Browse. And there select the data, which we look at here. So it's from I22, it's a silica 100 nanometers. thusFit, if you have some strange ASCII data files, you can modify here the input format if somehow the columns are differently ordered. It's symbol characters for the type of columns you provide. So X is a Q vector, Y is the intensity, and E is the uncertainty. You can also provide a couple of lines to skip at the beginning. And there's also here some unit conversion, I would say in quotes, because it just does some changing order of magnitude. So from angstrom to nanometer by multiplying by 10 or dividing by 10, for example. That's what it does. In principle, you have to know what you are measuring in. So the unit of your data, if it's nanometers, the parameters will also be mostly based on nanometers, and you have to check that in the overall formula, basically what units you're working with. This matters especially for absolute data. So when pressing OK, I get a window for merging files, or I can close this About window here by clicking on the logo. It gives us more space. So merge files allows us to load also different files and make a single curve out of them by merging several data files. But here we have only one, and hidden under the file name is a button for reduction options. So, reducing the point density for speeding up calculations later. So from SAX measurements, it's quite dense, as we can see here. We don't see any individual points anymore. And there are several options given for removing some points. So I can use here, for example, the relative distance in 2 dimensions, and I say the minimum distance, I increase the minimum distance between data points a bit, so it's only rough thinning out. And here I see already something happening, that it reduces this a bit to increase makes the calculations later a bit faster. Perhaps a bit much. And then we click OK, and this window goes away, and it gives us more space for the parameters to set up. By default, in the parameters window, we have spheres and polydispersity with a polydispersity by a log norm distribution given. So if we just plot this curve, we see already a model here in the background, and the default values are already a bit off, but at least the oscillations kind of fit, but are on the wrong place. So we have to shift it a bit. And the basic idea is improve the scaling. So this is rather close here already. But also I would like to move the minima more closer to another. So this can be done by the size of the particles. So if I remove the polydispersity and use only the sphere, I have here the radius parameter. If I plot this model, I see it has very sharp minima here, and I can increase this value. We know that should be approximately around 100. I guess is always a good start. Oh, that's really a lot. To remove the sharp minima here, I can enable the log norm distribution again. You get something as before. Because here if I go in the distribution function, it shows me the formula in the button right above the interrupt button here. It's a short reminder what the log norm function looks like, and the mu here is the parameter for the size of the particle. So it switched back to 10, and I can increase this to 80 to have a look, and it moves them much closer to another. This I can use to do the first fit by adjusting the scaling of the model. To doing this, it's always best to select a part of the curve and not the full curve, because at the beginning and the end of the curve you have often large error bars which make the fit unstable there. So it's best to select the middle part for fitting step by step. So in this case I would perhaps select this area. You can do this by pressing the shift button, and then with the left mouse button you can click and drag the gray region. And you can remove it again by pressing shift again and clicking in the plot window, removes this, and you have the full area again. So we select here only part of the curve and set here the n parameter for the scaling to fit, and once it's fit, and that somehow brings those curves closer together. Then I remove the selection again and apply the whole function here, the whole plot, to get not only the selected part but the whole curve here. So here we can see that it gets kind of close but still not so nice. So let's try to somehow further improve the radius or the size of the particles with the scaling. Let's see what happens. Doesn't bring it so much nearer. Here it got, what you want to achieve is basically to match the minima and the maxima of the curve. Yeah, this is perhaps the scaling is okay. Let's try to fit the size of the particles. That's not so good. So if the algorithm doesn't get that in the first try, we can try to adjust the starting values to get it closer to what we want to achieve. So here in the beginning of the curve we see there's a strong particle interaction, and that's why I want to concentrate on the lower part here. And then I fit again the scaling and the size of the particles in the polydispersity to match them more closer. For example, like that. And I deselect the area to see the whole curve. And now I get a better overlay of the model with the data. Now, what would be interesting here is to fix the starting part of the curve, the structure factor. For this, one could try a hard sphere, for example. It has the default values.
Good choice.
Good choice, okay. For the repulsion radius 100 and volume fraction, let's see how the structure factor looks by itself. Here I can, in the structure factor pane, I can switch to showing only the structure factor and pressing apply. Yeah, it plots it in the same window. The structure factor is always around 1. So this doesn't help me much. So let's plot the overall scattering intensity by including the structure factor. And we see that it damps kind of the beginning of the curve, but that's certainly not good enough. Oh, we are at around 50 because it's the radius, not the size. So I adjusted the radius first, and now I'm working on the volume fraction. It's pretty high here. So let's try a half, 50%. That matches really nice already. And we can try to fit this while fixing the other values in the pane. That's the same. We can remove the fit buttons here and make sure only the volume fraction is selected for fitting, and then we can run fit the whole curve to see if it improves this a bit. Not so much. Let's see what happens if I increase this more. Oh, this could be good, but yeah, so two options. One option would be, I see here, would be to switch from the monodisperse to the local monodisperse, so that it takes not an individual radius, but the radius from the sphere here. I hope that's true, yeah. And then we could try to fit the volume fraction to the beginning of the curve. This is rather slow. And perhaps select a larger area. And also perhaps optimize the size a bit, the size of the particles and the scaling. Let's see if it breaks something or improves it. Not really. You can also increase the polydispersity, but this often has unwanted effects because it might smooth the result too much. But here it progresses only very, very slowly. So going back to manual, figuring out this manually by reducing the volume fraction a bit, because it was really strong, lower than the actual measurement. We could keep the polydispersity and not fitting it, and have a look what happens. Yeah, this one is difficult.
Yeah, I don't actually expect you to get it.
Okay. Can you give a word on the volume fraction with this dense powder samples?
Yeah, it's a densely packed powder of spheres, which comes into the problem where I don't think you would be able to fit low Q with what people may seem as a complex model, but is currently not so complex because it's only adding a single structure factor and a single form factor. But when you're packing really nice spheres, they are quite nice spheres because, well, I made them. So, so yeah, but when you pack things like this together, you can also get other structure factors coming up from them rather than just a q to the -4. You can also get other things. So Ingo has actually done really well for a start. But what is the main thing you see for these? Lots of the bumps, they look like they are sort of two bumps rather than one bump. So when Ingo is just doing the sphere, and then when he adds the structure factor as well, we start seeing this extra bump in there. So that's why they all look really weird shaped. But yeah, what Ingo is doing is actually a really good example of how to do fits. You do one bit, and then test it, try it, find out if it makes sense. But yeah, Ingo is doing a very good job.
Yeah, but thanks. But as you can see, it's still some missing. There's something missing here in the beginning. So I concentrated then later on the middle part because the middle part really closely matches the minima and maxima of the sphere model. But you see that at the beginning there's a strong influence of the structure factor, which kind of moves the minima and maxima out of what the sphere should provide or show.
You probably need a Perot in there for like a background, and then you'd get a bit closer, and closer and closer. It's iterative and it can take a long time. Ingo has, so far I'm very impressed. So.
And do we want to do this with a Perot as an example?
Yeah, I think if you threw in a q to the -4, At your low
So-
Q, that will give you a bit more of the upturn.
Okay, wait a second. So it's what we discussed earlier. So I use a background, not constant. So if just to show here the option. So if the background function in SASFIT is kind of a polynomial. So in the lower part, you see the formula where you have different parts summed up. So the C0, the first part, is just a constant value. C1 is a linear value scaled with Q, and C4 is with C4 you can get a slope based on Q with an power or exponent. So the alpha is the exponent. So if I select 1 as background, for example, I get, now show all of it. Oh, we are at 10 already. So 1 is not, we don't see here. If I set 10, we see that it goes up a bit. So this is not what we need here. I can set this, to 0? Yes. What we want to have is, I think, at the beginning, Glenn, right?
Which side do you class as the beginning?
The beginning of the curve, the Q.
Low Q.
Low Q.
Low Q is so similar to what we did the other day.
Yeah, okay. Will it be linear or the C4 to Q minus 4?
I think alpha has to be 4. Not minus 4.
And then
Minus alpha, but 4.
4. Yeah, exactly. 4. So it's minus alpha, it's minus 4.
That should be at 1 at least.
You get 1.
Maybe 100 or so.
So we can see on the curve itself, I disable the first one, only show the second one, then I get this. So I have here only Q to the minus. So this is overlaying the first contribution. I enable the first again.
Yeah. Okay.
And we see this being improved a bit.
This sample is, it's complex. There's lots of things going on. But I also think it's a very good way of showing how SASFIT is. SASFIT can be complex, but it can also be very, very useful. And being able to switch on and off models sort of in an instance is also very good for the fitting process, so that you can build up it's very easy to build up a complex model with SASFIT.
Thank you very much for your attention.